Hi, this is Bob Westervelt. I'm happy to introduce Joshua Yang today, who will be telling about an exciting new field for parallel computing for AI and machine learning. And that's based on memristors, where the resistor actually remembers its previous state and sort of a combination of a memory element and a processor. Professor Yang got his doctoral degree at the University of Wisconsin-Madison, and they went on to HB Labs, where a lot of the initial memristor work was done between 2007 2015. Then moved on to the University of Massachusetts at Amherst, and then recently was appointed in 2020 at USC. So we're very happy to have him here, and I look forward to his talk.
Many thanks for the introduction, Bob. And also thank you for organizing and kind invitation and to talk about our work on memoristic materials for computing. So as the title suggested, I'm going to first briefly introduce memoristic materials and devices, just for those who are not familiar with this topic. Then I'm going to mainly focusing on how to use such devices for computing. The computing I'm going to talk about are mainly bio-inspired computing rather than quantum computing. So let's first look at the background. So basically the challenges facing the future of computing. First, at device level, we know Moore's law is coming to an end, right? So TSMC is working on 3 nanometer technology node, and how far this can still go. That's one big constraint, the Moore's law. And the second one is the memory war. Basically, it is the performance difference between memory and the processor is keep increasing. So basically memory development is behind and still behind, and the gap is increasing actually. The third is the Dennard scaling law has ended about 10 years ago, which means even if we can keep cramming more devices on the chip, but we cannot turn all the devices on simultaneously because the power density is not scaling anymore. The power density increasing quickly, and if we turn on all the devices simultaneously, we're going to burn the chip. That's why we keep some part of silicon dark. It's dark silicon. Right? So those are at a device level, the challenges. At architecture level, the challenge is as big, if not bigger. Actually, that is the Von Neumann bottleneck. We know our traditional computer is built based on Von Neumann architecture, which features the separate memory and processor units. So you store your information in the memory unit. When you need to process it, you take it to the processor, get it processed, send the result back to store here. You take the next piece of information to process. This was perfectly fine in the past when computing did not involve a lot of data. But nowadays it is the big data era, and most of computing is data centric. Then shuttling a lot of data constantly between the two units costs a lot of time and energy. And this is a sequential process. It doesn't help to process a lot of data. And also it's an analog system, a digital system. Our world is analog. So you need to convert analog into digital, then get processed. The conversion between analog and digital is also known to cost a lot of time and energy. So in order to deal with this problem for processing a lot of data, we learn from the most efficient tool known for doing this so far, that is the human brain. And the brain can be viewed as a network of neurons. So you store the data in the network, and you process the data where it is stored. So it is in-memory computing. You do not need to shuttle data anymore. And also the computing can happen everywhere simultaneously in the network. It is a parallel computing instead of sequential. And also it can deal with analog data directly. It is analog computing. So with these three components together, you're going to have a very efficient computing accelerator to deal with big data. There's more, actually. The brain is also known to be very efficient in learning. It can learn with very low energy consumption, with very few examples, because it uses some neuroscience principles to do that. If the artificial devices we built to make the artificial neural network can also implement such neuroscience principles, then it is hopeful to get advanced intelligence and something maybe close to natural intelligence eventually. So in order to implement such a new computing paradigm, we need a new type of devices. Memory-safe devices turn out to be one of the leading candidates. So using memory-safe devices for computing has been the research focus of my group in the last few years. Some of our major results are summarized here, which can be categorized into three groups. In the first group, we are trying to just build a machine learning accelerator. So trying to get higher energy efficiency and higher throughput. In the second category, we're trying to build a more faithful artificial synapse, artificial neurons, artificial dendrites, and so on and so forth. We put them together to form a more faithful artificial neural network. Hopefully that can lead to advanced intelligence. And in the third category, we're trying to just build a tool set for intelligent system. For example, here you're seeing a single device, a pressure sensor, and talking with a single device that is a processor. So basically you can have two nano devices in principle to form the most compact sensing system, something like that. And now let me switch gear, briefly introduce memory-safe devices, which is also called RAM when it is used for memory application. But for memory application, what we care are mainly the static ending states of the switching. But for computing application, as you will see, for some type of computing, we also needed to use the dynamic process of the switching. So the memristor is a dynamic device that is the emphasis to be made, different from RAM. So the device itself has a very simple structure. It has a functioning dielectric layer with two electrode, metallic electrode. The functioning layer could be oxide, nitride, sulfide, a lot of type of dielectrics. The structure is simple, but it has rich materials, physics, chemistry, electrical issues, which give us a rich device behavior for different applications, but it also gives us the headache in understanding the device mechanism in controlling them for real applications. For real application, we usually use a crossbar structure like this. And here you're looking at 17 of such crossing point device. At each crossing point, you have one device. If you cut the device open, look at the cross section vertically, you can see you have a thin dielectric layer with two metallic electrode. If you apply electrical bias between the two electrodes, you are going to introduce some change in the materials. And such change can lead to either capacitive change or resistance change. And the resistive change will lead to something like this. It's a hysteresis loop in the current voltage plot, which is a signature of memristor. And you follow this IV curve. Initially, the device in the off state with low current, and at a threshold voltage, device is turned on. Then it follows this curve, become conductive. If you want to change the device back, you can use opposite voltage. When it is high enough, you switch the device back to high resistance again. So such type of switching has many promising properties, such as it can happen really fast. We have shown that we can switch device on and off repeatably within 85 picoseconds. And it is also very scalable. As you can see here, recently we made a device at 2 nanometer by 2 nanometer size, and we even make a little crossbar array of that. So between on and off states, it has many, many intermediate resistance levels rather than a binary. It has it is multi-level, and that's great for memory application and also for synapse application. You want it to be analog. In addition to be scalable at 2D, it is also stackable in 3D. And as you can see here, we can stack the device on top of each other because they just need amorphous or polycrystalline material. And so in this example, we stack 8 layers of memristor to build a 3D neural network. And we even use that neural network to serve as a convolutional neural network to process video information. So there are other good properties such as CMOS compatibility, non-volatility, non-destructive reading, so on and so forth. I'm not going to go into detail on that. Rather, I'd like to also talk about the challenges facing such a device for real application. The first one is the mechanism understanding. So after years of study, believe it or not, actually there are still a lot of missing holes in the understanding of the switching mechanism. The reason it's so difficult is shown here. First, whatever changes during the switching responsible for the resistance change is buried underneath the top electrode. So it is invisible for some of the materials characterization tools. And also, whatever changes in the material is localized both laterally and also vertically. It can be in a very tiny region. And to make it even harder, such change can change location randomly. And so from switching cycle to cycle, the location can be different. And from device to device, the location can be different. So you all also know that this switching can happen within a really short time, like a sub 0.1 nanosecond. So all these together make the understanding or visualize the switching process very, very difficult. However, different from memory application, for computing application, as I mentioned, we want to understand the entire switching process, and we even want to use the switching process itself for computing. So that requires some in situ characterization techniques with very high spatial and very high temporal resolution to visualize the process. So this is very difficult, but after many years of study, we do have a decent understanding in some material systems, such as a model system, titanium oxide. So titanium oxide switch, shown here, you can view titanium dioxide as a semiconductor with wide band gap, 3 eV band gap, for example. As a semiconductor, it can have its own dopants. In this case, the dopant can be oxygen vacancies. So oxygen vacancies are known as N-type dopant. It is positively charged. Different from the dopant in silicon, the oxygen vacancy dopant here, they are mobile. In the silicon, the dopants are immobile. Here, they are electrically mobile. You can move them, which is the basis of the switching. So you have the doped region, which are conducting, and the undoped region, for example, at the metal semiconductor interface, you have a Schottky-like contact, which give you high resistance. And that's why the entire device is in the off state. So now if you want to change the resistance, you can use the electrical field to move the dopant, also dope the interface region and remove or reduce the Schottky barrier. So you get the conducting on state. And if you want to switch the device back, you use offset voltage, you move the vacancy back and clean this interface, recover the Schottky-like contact, you get the off state again. So in this example, oxygen vacancies are the mobile dopant. You can use other type of mobile species. For example, you can use silver in silicon nitride oxide to build a diffusing memristor. I'm going to talk about that later. And you can use other mobile species such as ruthenium in oxide, which turn out can give us a low current analog switching device. I do not have time to talk about that today. So basically, the switching is a result of ionic motion and the combined effect of electric field, chemical potential, and Joule heating. Some oxide, such as titanium oxide, the electric field plays more important role. In other oxide, such as the niobium oxide, Joule heating play more important role in the switching. So under those driving forces, the ion motion can take a different mechanism. For example, the charged particles can be moved by electrical field. We call it drift. And the kinetic energy of electrons can move ion. We call it electron migration. And if you have an ion concentration gradient, at elevated temperature, the ion can move against the gradient. And that's fake diffusion. And even the temperature gradient itself can move ions. That's thermophorescence. So it is not uncommon, actually, in a single memristor, multiple ion transport mechanism are at play. So that again give us, of course, rich device behavior. That's good, but also give us the difficulty in understanding and controlling the device. So there are other challenges, such as if you use the device in a large crossbar array, in addition to memristor, you also need something called an access device to work with each memristor so that you can randomly select one device in the array to operate. And you need a selected device. I do not have time to go into detail, talk about selected device today. Rather, for the crossbar arrays, I'm going to show you later in the examples, we use a transistor as a selector in the crossbar array. And another challenge is for computing application, we need to engineer some desirable dynamics, such as ion diffusion dynamics for computing. I'm going to touch upon that in the next section, talking about how to use those devices for computing. So now let's switch gear, talk about the bio-inspired computing with such devices. For such application, you can have different levels of bio-inspiration innate, very little or some, and a lot more bio component in the computing. I'm going to give an example in each case to talk about the computing. First, let's look at the case with very little bio-inspiration in it. In this case, the memristor device is just a resistor, and they form a resistive network for computing. And the goal for such computing is to accelerate vector matrix multiplication. no other purpose, just to accelerate vector matrix multiplication, which may sound trivial, but actually it is a very, very big deal for machine learning because depending on the algorithm, actually most of the machine learning algorithm, the computing effort, over 80% or 85% of the computing in the machine learning algorithm is really vector matrix multiplication, which unfortunately is something our digital computer is not good at, because in order to compute vector matrix multiplication in the digital computer, what you do is you multiply every element in the vector with every element in the matrix, and you do that one by one, then you add the result together to get the dot product. And if the matrix is large, it has many, many steps. And more importantly, you store all the computing parameters in the memory. And during computing, you need to frequently visit the memory, fetch the data, which costs a lot of time and energy. However, if you do this in the memoristic crossbar array, you can finish a vector matrix multiplication within one computing cycle, regardless of the matrix size. So this is how you do that. You can program the conductance of each cell in the array to represent the mathematical value in the matrix to be multiplied. So then you can also use the amplitude of the input voltage to represent the mathematical value in the vector to be multiplied. So to perform a vector matrix multiplication, you just need to apply the voltage to the rows simultaneously, and you collect the current here. That is the dot product. That's your computing result. Because at each crossing point, you can see you have a voltage applied to a conductor, you get a current here. The current is really the multiplication result of the voltage and the conductance. In other words, Ohm's law has done the multiplication for us. It happens everywhere simultaneously. If you collect the current here, you are adding those current together simultaneously. In other words, Kirchhoff's current law has done the accumulation for us. So basically, you apply voltage, you collect the current here, you get your computing result within one computing cycle. So this can is really in-memory computing, parallel computing, and analog computing. That's why it can lead to orders of magnitude improvement in speed and energy. In order to demonstrate that, we build our hardware. This is the wafer and zoom in of the circuit, zoom in of each cell. It has a transistor as a selector combined with a memristor in series. So we can freely program the array to something like what you just saw. The pattern is a DCT, discrete cosine transform operator. You can use those to perform linear algebra acceleration. So for example, you can do image compression. This is the original image. This is the image compressed using the crossbar array I just showed you experimentally. And to compare, we also compress the image with software to the same compression ratio. As you can see, they are quite comparable. So this is cool. It is much more efficient to perform computing. But again, like I said, the memristor here is nothing but a resistor array, right? So in fact, the memristor can do more. It's more than a resistor array. For example, it can be electrically reprogrammed. In other words, it can perform some sort of learning in the network. So those are higher level of bio-inspiration unit. And let's first look at what are the key ideas for bio-inspired computing. The brain, again, can be viewed as a network of neurons connected by the synapse. And then when a synapse are active, we call it fire. And when it will send signals to its neighbors. And if there is a neuron such as this one, it receives more signals from its neighbor, itself become active or it fire. If two neurons such as these two, they are active around the same time, or they fire around the same time, the connection between these two becomes stronger. So it's called a fire together, wire together. This is believed to be a fundamental learning rule in the biological neural network. It's the High-Beam learning rule. A specific variant of it is the spike timing dependent plasticity STDP learning rule. So now suppose these neurons are active when you see a fluffy animal with big eyes, small ear, and a pointed face. And around the same time, if someone, like your mom, says cat, this will excite additional neurons, such as this one. And those neurons are active around the same time. The connection between them becomes stronger. And next time, when you see a similar animal, this neuron will fire quickly to help you to recognize it. So if it is a dog, it's probably associated with a slightly different group of neurons. So in this way, the neural network gradually learning by changing the connection strengths between the neurons with examples as the input. So using similar ideas, we're trying to train our crossbar memoristic network as a neural network to recognize patterns such as the handwritten digits. So in order to do that, we first partition the crossbar array we built into 2 layers of neural network. And the output of the second layer has 10 neurons corresponding to the 10 handwritten digits. Then we can convert the pixels of the picture into analog voltage to serve as the input to the first layer of the neuron. Because initially these synaptic weights or memoristic resistance here are random to begin with. Regardless of those input, these 10 neurons fire randomly. So now we can use some algorithms such as backpropagation to figure out how to change the synaptic weights here, then manually change it by switching the memristors so that whenever the input is 0, the first neuron fire. Whenever the input is 1, the second neuron fire, so on and so forth. We train the neural network with many examples, such as 1,000 examples, 10,000, more than that. And using those examples to train the network by switching the memristors in the network. And as you can see, eventually, after thousands of training examples, the network become pretty good at recognizing unseen patterns, similar handwritten digits with over 90% of accuracy. And so using similar idea, this could be very useful. And in addition to the image compression, the pattern classification, we also use it as a convolutional neural network for video processing. We use it as a long short-term memory network to accelerate gate classification. And we also use it as a convolutional long short-term memory network. Also use it to accelerate reinforcement learning, so on and so forth. So these are cool and powerful, but it also have problems, right? As you already seen that the training of the learning is very costly. You need many extra computing to figure out how to change the synaptic weights. And you need many examples to train the network, and using a supervised learning approach. So we know our brain can do much better. We only need a few examples to learn. And also we do not have the weight calculation, then change the synaptic weight in a supervised way. Rather, we believe in the brain, we are learning in the neural network is changing in a more like unsupervised way. So in order to make the learning more efficient, we need something more than just a non-volatile memory. And so far in the two examples, we know Memristor is a non-volatile memory, and it's a reconfigurable memory, that's it. But in order to perform more advanced functions, such as unsupervised learning, we needed the device to be more capable, more than just a non-volatile memory. So we learn from the biological device, such as the biological synapse, to see what features we need in order to perform more advanced function. So one thing we learned shown here, this is a synapse with the pre-neuron, post-neuron. The synaptic weights are really how many ion channels or how conductive of each channel. So that's the synaptic weights. It's more like the non-volatile memory component here. But in order to change the synaptic weight in the synapse, it needs to go through a dynamic process. So it goes like this. You need a pre-spike, which need to be large enough that can open the so-called NMDA channel, ion channel. Once this ion channel is open, then the calcium ion can diffuse through that channel, go into the post-neuron. This is the diffusion process and diffusion. Once the calcium get into here, it can trigger some bioactivities to install more ion channel or make the existing ion channel more conductive, basically update the weight. But before getting here, you need to go through this dynamic process. As you can see, the process is controlled by some diffusion of ions. So in other words, in addition to the non-volatile memory, we also need another component in the synapse to control the dynamics. It's better to be a diffusion dynamics. So do we have such a device? If we think about a Memristor, actually there is one type of Memristor we developed. We call it diffusive Memristor, and it has the diffusion dynamics we need. This video shows at an atomic level what's going on inside the diffusive Memristor. You have the two electrode, you have a silver doped in silicon nitride oxide. When you apply electrical bias, you can see silver are moving and eventually form a complete ion channel. And after that, when you remove electrical bias, the silver actually go back, the ion channel breaks. So you may not see that clearly in the video. You can see better in the snapshots here. So initially, between the two electrode, there's a gap, and the current between the two electrode is very low when you apply electrical bias. But over accumulation, you can see silver are moving, and those are silver moving into the gap. And at this moment, silver form a complete channel bridging the top and the bottom electrode, and the current jump to a higher level. And the channel size is about 4 nanometer in diameter. So after this electrical bias is removed from this moment, you can see under zero electrical bias, the silver conduction bridge actually breaks by itself. The silver ion move back, and eventually it forms a sphere shape here from a filament to sphere. And zero electrical bias, we know that's a diffusion process and driven by the interfacial energy minimization between silver and the dielectric material. So this dynamics can help us to build a more faithful synapse. So we integrate that diffusing memristor into this device that's a non-volatile memristor. So these two combine to form a synapse with dynamics. So with such dynamics, as shown by those electrical measurement data, the device can naturally reproduce the short-term plasticity behavior observed in the biosynapse long time ago. It's quite complex short-term plasticity, but it can be naturally reproduced by such device. And for the long-term plasticity, especially the spike time-independent plasticity, with the dynamics, the device can naturally show such behavior without the need of playing tricks in the input signal or overlap the input spikes or change spike shape or something like that. You can just do it like what you do in the biosystem, give the spike to the synapse, it will naturally show the STDP learning behavior. And that's synapse. And in order to build an artificial neural network, we also need neurons. And we know the main function of neuron is to generate action potential like this. So initially, you have the ATP pump that can pump sodium ion out of the membrane and pump potassium ion in the membrane. So you have a sodium ion gradient across the membrane. You have opposite gradient for potassium ion across the membrane. And you pump every 3 sodium ion out, you get 2 potassium ion in. So eventually you have a net negative potential inside the membrane. So that's the resting potential. And now if you have input electrical stimuli, and you can see the membrane potential gradually increase. Once it's over a threshold, it suddenly opens the voltage controlled sodium ion channel. And once this ion channel is open, sodium ion flood into the membrane driven by the concentration gradient built by ATP pump. Then a sodium ion goes in and your membrane potential increases dramatically. And then sodium ion channel close. Even before it closes, the potassium ion channel opens, and potassium ion flood out of the membrane, also driven by its concentration gradient. So the sodium ion, potassium ion go out, the membrane potential drop, even have an overshoot here. And then the potassium ion channel close, and under ATP pump, the neuron goes back to its resting state after this firing process. So this turned out this process can be closely mimicked by the diffusion memristor case. You can see from here to here, it emulates the process of accumulation, and channel still is closed. And at this moment, after you accumulate over the threshold, the ion channel suddenly open, and you have a high current. It's like the ion channel open process. After this, without electrical bias, you can see the sodium, the silver goes back, and the ion channel close automatically, driven by the diffusion and the minimization of individual energy. So basically, we can use the diffusion memristor to mimic the ion channel in the neuron, and we can use a capacitor to mimic the membrane capacitor here. So this capacitor can be an intrinsic capacitor of the diffusion memristor, and it can also be an external capacitor. So with these two, and we can build an artificial neuron, and the electrical measurement data here shows this artificial neuron can have the very nice decay, integration, and fire function, as can be seen by those electrical testing data. So now we have a more faithful synapse, more faithful neurons. We can build a neural network by putting them together. experimentally, and we have this small neural network. Even though it is small, but with the more advanced synaptic neuronal functions, it can already perform something amazing, such as unsupervised learning. So in order to demonstrate unsupervised learning, we need two of such neural network. So the first layer has many convolutional layer. Each column is a kernel. The first layer serves a convolutional layer with those kernels at each column. So those kernels can extract features from the input pattern, and those extracted features are represented by the firing pattern of the output neurons. And such output firing pattern of the first layer serve as the input to the second layer of neural network. The second layer of neural network has 3 neurons. In this case, we're trying to use 3 neurons to classify 4 input patterns. Initially, because the synaptic weights here are random, regardless of the input, these 3 neurons fire randomly. And if it is a supervised learning, we would use back propagation to figure out how to change the synaptic weights, then manually change them. But for unsupervised learning, we don't do that. In fact, we don't do anything but repeating those input. Let the network evolve by itself through the dynamic interaction between the synapse and the neurons. So they sort of perform self-organization through the Helbing-like learning rule. So as you can see, with each input, the synaptic weights change gradually. And after only 30 cycles of training, the synaptic weights evolve to a degree so that whenever the input is A, the third neuron fire, not random anymore. Whenever the input is S, the second neuron fire. Whenever the input is U and M, first neuron fire. So it turned out this small neural network thinks U and M are close enough to be put in the same category. So this is a small neural network, and it already shows very encouraging result once we add the neuromorphic dynamics into the device. So this is a baby step, but it indicate, this is going to be quite exciting along this direction. So I'm going to use a couple of slides to summarize some of the ideas. So we know CMOS are very powerful. You can use it to build almost anything, including neural network. But the CMOS device were not created or optimized for this purpose. It's not efficient. It takes about 10 transistors to simulate, not even emulate, a synapse. It takes even more transistors to simulate a neuron. But we have a lot of synapses and neurons in the brain. If you do a rough calculation to simulate all the synapses and the neurons in the brain, you would need more than 10 million the state-of-the-art chips. So this is obviously not practical, if possible at all. So fortunately, we have those emerging devices, as we have seen, such as a diffusive memristor or drift memristor. You only need a couple of such devices to emulate a neuron or synapse. And such device can be even smaller than the biological synapse and neurons. So this could be a promising approach. So the reason the CMOS devices are not very suitable for this purpose is shown here. If we think about our CMOS device, it's silicon defined by the dopant profile. The dopant profile are really ions, right? But those are static ions. They do not move after fabrication. During electrical operation, you're not moving ion. You are moving electrons, which is fast but volatile. It's good for logic, but not for memory. So since the hardware are not changing during learning, the learning is really software learning. And this is very different from the biological system. So now imagine if we can mobilize those ions electrically, so we can move those ions to change the dopant profile to get different type of devices on fly during learning. So that will actually open a window for almost infinity opportunities. Now we have a new type of devices, just like a memristor. So here we are manipulating ions, which is slow but non-volatile. It's better for memory application. And during the learning, you have the hardware are changing. We can really realize the hardware learning, and the dynamics of the ion motion is very similar to the dynamics of the ion motion in the biological system, which play very important role for the process in the biological neural network. So the similarity may eventually allow us to approach something like the natural intelligence. So here the caveat is that even though we know how to precisely control the position of the ion during the fabrication process, after decades of study and development, we do not really know how to precisely reconfigure the dopant electrically yet. So that is challenging. That need to be solved in the future to develop the post-CMOS devices. And on the other hand, if you think about the devices in the brain, they are pretty lousy devices. They are slow, they are big, they are stochastic, they are inaccurate, and yet they can perform amazing computing. That is because they have their suitable corresponding architecture and algorithms to work with those neurons. So the co-design between the device and the architecture algorithm are critical. In order to do that, we needed to understand better how the brain works, which we have very limited knowledge so far. That is another thing really need a breakthrough in the future. Okay, so I guess the take-home message, the big data era give us the challenge in the computing, but also give us opportunities to develop unconventional computing paradigm. So you need new devices for the unconventional computing. There are a number of candidates. Memoristic devices is one, which can be fast, scalable, stackable, analog, and promising for bio-inspired computing. And the switching mechanism of the memoristic device is very different from the CMOS device because it involves the migration of mobile ions. And so there are a lot of work need to be done in order to precisely control the ion motion electrically. And yet we have demonstrated memoristic arrays that can that have shown orders of magnitude higher energy and throughput over the traditional CMOS approach. So with some supervised learning and such memoristic neural network can perform pattern classification, can serve as LSTM, reinforcement learning, so on and so forth. And with a higher level of biocomponent in the device, and we can even see some more advanced learning, such as unsupervised learning that has already been shown experimentally in the new type of memoristic neural network. Finally, I'd like to thank my postdoc students for doing the work, really, and my coworkers from a different institute. And also like to thank my sponsors for supporting the work. And also I'd like to thank you for your attention. I'll be happy to answer questions if you have any.
Okay, well, thank you. Very much for an interesting talk. For people who would like to ask a question, the way the software works is you need to type it into the chat, and then I'll read them and can answer them. We have a few already. JB Groves says the array you're speaking of is the massive parallel vector array. How large can the array be?
Right, that's a very good question. So so far, I think the largest array we have built is 256 by 256. That is already good for many tasks, but for even larger array, matrix, for example, you deal with, you can have a multiple core, multiple arrays work together to deal with those. So the reason we choose such size, on the one side, there are some device limitations. On the other side, it's also to keep the balance of flexible and efficient of the system. Because in many cases, you're dealing with a smaller problem. If you use a too large array, you're wasting some resources not used. But also on the other hand, there are some limitations, such as the wire resistance in the array need to be solved. Really, you need to make the device more resistant, much more resistant than the wire, so that you can reduce the impact of the IR drop on the wire. So you make your array larger. So of course, there are other, if you use the ADC-DAC driving circuit, then how much current the ADC-DAC can take per column or row is another limitation. So the short answer is you have seen many groups doing 128 by 128 arrays size like that. We have 256 by 256 at this moment. I believe it can be made larger in the future. At this moment, it's 256 by 256 with multiple arrays together to deal with larger problems.
Okay, thank you. Another question from Yuan Vigo. Is it possible to design a memristor with semiconductors and liquid metals with magnetohydrodynamics, MHD, at the micro scale level, tin, gallium, maintaining bio-inspired criteria? Question mark. What would be the problems to face with the case of MEMS with MHD? Question mark.
Yeah, I'm not sure I fully got this, all the details of this question, but yeah, so as long as you have the ion motion and that has impact on your electron transport, you get a memristor. And that, as we've seen, it has a lot of similarity at a physical mechanism level with the biological system. I would think, such system is interesting to explore. Although I don't know, all the detail, it must have some advantage and disadvantages when you go into, the detail really doing it. So I don't know if I answered the question here.
Okay. Okay, well, thank you. A third question from Pagi Kim. According to Leon Chua's definition of memristor, is a two-terminal electrical component relating charge and magnetic flux. If we generate some charge difference in your memristic devices, could we measure magnetic flux difference? Question mark. Could we experimentally measure the memristor value using these memristive devices?
Yeah, so it is a little bit confusing, in the original definition of the memristor, it is flux. It's not necessary to be the magnetic flux. In fact, in those device, it does not really has a magnetic component in it. It's just the integration of the current is a charge integration, time integration of the voltage lead to flux. So I do not think we can really measure some magnetic properties in most of the devices I have seen. Yeah, so what's the second part of the question?
Well, what would be the problems to, oh, excuse me, I'm reading the wrong one. Just a second. Could we experimentally measure the memristor value using these memristive devices? I think yes.
Yeah, we can, yeah. So there are a lot of properties we can measure, memristive value, current, voltage. I doubt magnetization, something like that. No.
Yeah. Okay, great. Any last questions? Type quickly. Okay, I don't see any, but this is very interesting stuff that I've been following for a while, and you've really taken it quite far. And so a very interesting talk. Danhee says hi. Danhee Ham.
Yeah, thank you. Yeah, good to see you all. Yeah.
And thanks very much.
Okay, thanks. Yeah.